I'm gonna share the screen and thank you for the very nice words to everyone. And it's been a great pleasure for me to be catapulted in such wonderful environment. And I will never be so enough. I will never show enough gratefulness for how I feel in this moment and how I felt in these years. Okay, let's go to talk about the title of this thesis first. The title of this thesis is Complex Contagion in Social Systems with Distrust. It's a very strange title, actually, because it contains very keywords that are built on top of the other to build an actually a bit cumbersome model, but if broken into pieces, the idea is very simple. We talk about social contagion processes, so processes in which individuals in a network, in a social network, can be persuaded to adopt or reject a social norm, an idea, and so on. The contagion is complex. Complex means that individuals can be infected individuals, indeed, by group interactions. And we will tell what does it mean exactly with distrust. And this is the main output of this thesis. So incorporate these models that are well known in literature and that are known in literature that have been developed with the context of trust and distrust in social systems. To give a brief outline, we will briefly talk about dynamics on networks, and then we will go immediately deep with the model that is divided into two different models. The first one is sign complex contagion, is the basic one, the principle, the initial one actually, and the second one is a variation, and we will go deep in that takes into account social balance theory, which is a sociology theory about how trust and distrust is distributed in social relationships. And then we will give some results and conclusions. Let's start by saying that networks and complex systems are basically everywhere. Many physics problems involves a huge amount of degrees of freedom, and so we are forced to seek for a statistical behavior, a statistical averages, so an average behavior of the system, and to show also emerging phenomena or collective behaviors. And networks are very useful in the sense that their definition is so general that they can fit perfectly and describe, they capture the dynamics and also the properties of a model in the sense that they describe how units behave and how units interact. For example, the mathematically a network is defined as a graph, which is an ensemble of n nodes and l links. Links in a network are a couple of nodes. And the main tool for describing the topology, the microscopical structure of a network is the adjacency matrix, whose entries are +1 if there is a node between two links. So if there are two nodes, so there are two nodes are linked is 1, or 0 otherwise. Let's immediately talk about dynamics on network, because this model is built on top of two principal components. We have the topology of the network. So we have a social structures in which nodes are individuals and the interactions, the links are the interactions between individuals. But then we have also to talk about the dynamics, which is a spreading dynamics, a social contagion dynamics. So we have a disease, a social disease, which can be an idea, behavior that spreads on top of the network and spreads both along the links of the network and also in group interaction, and soon I will be more precise. The most paradigmatic example is the SIS model. It's a pairwise interaction model, social contagion, one in which we associate to each node a binary random variable. So we divide our population of nodes into two broad categories. The susceptible nodes, which are the nodes that can be infected in the sense that can be persuaded to adopt the behavior, and the infected nodes, which are the ones that spread the behavior actually. Defining the density of the infection of node I at time t as the average over many stochastic realizations of this binary random variable, we can write the master equation, so-called, of the model, which tells us how this density of the infection of node I at time t evolves in time according to the reactions that take place on top of the network. So what I meant before was two levels, in the sense that we have the topology of the network, which we are going to simplify actually, and the dynamic itself that have a non-trivial interplay, of course. The principal approximation that we're going to do in this thesis are an homogeneous mixing assumption to simplify this master equation, because they are n couple differential equations, so it's quite hard to solve both analytically and computationally. We're going to assume that all nodes are statistically equivalent one with the other, and we're going to use a mean field approximation, an homogeneous one, saying that the density of infection of node I is equal for every node, and so the degree, so the number of neighbors connected through node I through a link, is equal for each node. So we're losing information about the topology, but this allows us to simplify this model into one single equation. And this is quite easy because what we do when we have such a dynamical system is look the behavior of the dynamics for large times, so the stationary state of the infection. And in simple model, we see that depending on the strength of the infection, the measure of the strength of the infection is this lambda, which tells us how many people on average an infected individual infects before healing. Depending on the value of this lambda, we have two possible behaviors. If lambda is less than 1, then the epidemic is going to die out in the stationary state, so for large times, regardless of the initial condition. Otherwise, there is a in the system, in the sense that the stationary state, at the end of the process, some finite fractions of the nodes will be infected. Let's model group interactions. As Professor Latora said, we model group interactions, in our case, with using simplicial complexes. There are many models many ways to talk about complex contagion. There are threshold models, but the one we took into account is simplicial complexes, in a sense that we generalize the idea of a graph, of a network with nodes and pairwise interactions. We define a simplicial complex as a collection of simplices, and a K-simplex is a set of K plus 1 vertices. So we perfectly have the structure of a network for K equal to 0, in the sense that for K equal to 0, we have for K equal to 0, we have nodes, okay? In the sense that we have a collection of one vertices, so nodes. For K equal to 1, we have links because we have collections of 2 nodes, and this is the definition of a link. For K equal to 2, which is the one in which we stopped, but the idea can be perfectly generalized to higher order structures, we have full triangles, in a sense that we model the group interaction, which is crucial in social systems, because differently from biological epidemics, social contagion occurs it is very reasonable to assume that social contagion occurs on group interactions rather than pairwise interactions. I'm much more prone to be convinced to adopt an ideology if I'm convinced by a group interaction rather than by single individuals. And two simplexes model full triangles. Why do I say full? Because the collection of the 3 nodes represents the simultaneous interaction of the 3 nodes, where the simplicial complexes have a closure condition, in the sense that for each simplicis, also the subsimplices belong to the simplicial complex, in the sense that if we have a full triangle, if we have the face of the triangle and we have a simplicial complex, also the 3 pairwise interactions forming the sides of the triangles will be part of our model. What is the idea of this thesis? The idea of this thesis is not only introduce the concept of social contagion on higher order interaction that is studied in literature, that has been studied by Professor Latora, but also the idea of trust and distrust in social systems. People are more likely to be convinced to adopt an ideology if they talk to someone they trust. And people are more likely to reject an ideology if they talk to someone they don't trust and who shares the same ideology. This is the basic idea, and this is very simple. How do you model that? We model that by assigned adjacency matrix, so assigned network in which each link is assigned a plus sign if the nodes belonging to this binary interaction trust themselves, or a minus sign if the 2 nodes do not trust, the 2 persons do not trust themselves. But also we assign a set of signs to the triangle interaction, to the 3 body interactions. We have to generalize the reactions that took place in the SIS model, because actually in the SIS model, we saw that we had 2 parameters. There were beta, that is the infection rate, and mu, that is the recovery rate. So an infected node at each time step can recover with a probability over time that is equal to mu, and a susceptible one, if in contact with an infected individual, can be infected, so can be persuaded to adopt the ideology with a probability beta. In this case, we have to differentiate the pairwise interactions depending on the signs of the links. So depending on the fact that the 2 nodes trust or distrust themselves. We still have the recovery rate, which is the top figure, which tells us that the blue node is an infected node, and each time step can recover with a rate mu. We have also that a white node, which is a susceptible node. If you look at the figure, maybe again, a white node Okay, awareness which is a susceptible individual, if in contact with with an infected individual and these two individuals trust themselves, the susceptible nodes can become infected with a probability beta 1. Similarly, two infected nodes that are linked, so they are interacting, and that do not trust themselves, one of the two susceptible individuals can switch to the infected individual can switch to the susceptible state with a probability beta 2. Similarly, we have to introduce higher order contagion processes with signs. Don't be scared by this picture, but basically the main idea is that these three top reactions that take place on top of the dynamics are the three body infections. So three nodes, of which one is susceptible, interact simultaneously, and the susceptible nodes with a probability gamma 1 can become infected. These two instead are nonlinear recovery processes, three-body interactions, and infected nodes that do not trust the other two can become susceptible, so can reject the opinion. Moreover, because of the fact that we are trying to model the concept of trust and distrust of a network with signs, we have different rates depending on the specific configurations of signs. For example, the three nodes here all trust themselves together, and then the susceptible nodes can become infected with a higher rate, with a higher probability over time with respect to the case in which, for example, the two infected nodes do not trust themselves, or in which the susceptible nodes directly experience the distrust with an infected node. Of course, I'm less prone to adopt the ideology if I don't trust one of the two people I'm talking to. Same reasoning for the nonlinear recoveries. What do we write? We write now the usual master equation in the same approximation that we talked before. So mean field approximation, homogeneous mixing assumptions, and we have this equation in which we have the recovery processes and the pairwise interactions that are the infection, the pairwise infection, an infected node encounters a susceptible one, and the pairwise recovery. But also we have the three-body contagion processes in the second line, and the three-body nonlinear recovery processes in the third line. For example, in this sketch I made, these are triangle interactions, these are links. This is a tetrahedron that we do not consider in this model, but this can be generalized. The main assumption that we do, the main parameter of this model, on the first version of the model, is eta. That is a global parameter, and that is equal to the fraction of distrust of a network. So it's equal to the ratio between the number of negative links of a network divided by the total number of links. So it's a ratio, and it's a number between 0 and 1. It's a global. It gives me global information about the amount of distrust of a network. 1 minus it, of course, is the fraction of trusted relationships in my network. And the fact that we are using simplicial complexes, so we are sure that if we have a triangle, then we automatically must have the three links that are forming the triangle, allows us to write not only the average number of links with a minus sign with zero positive signs. This is the average number of links in the network with 0 plus signs. This is the average number of links in the network L1 with 1 plus sign. And this is true, but we can also write the average numbers of triangles tau with 0, 1, 2, and 3 positive links as a function of eta. So we are capturing the information about the topology of the network in three different parameters. Eta, the amount of distrust, our proxy for the distrust of a network, the average connectivity of the network, K, and the average number of triangles in the network, average K delta. What we see is that if we solve the model, if we find the stationary solutions of this model, we have a new phenomena arising, a new emerging phenomena that arises in this model, in the sense that if the infectivity over the triangles is small enough, in particular smaller than 1, this 1 plus lambda 2, where lambda 2 is the rescaled infectivity, average K times beta over mu for the recovery, pairwise recovery process. And if this lambda tilde, which is equal to lambda 1, the same as the SIS model, times the 1 minus eta, which is the fraction of trusted links, this lambda 1 delta is smaller than 1, then only the disease-free solution will be possible, in the sense that regardless of the initial condition, the epidemic will die out. Contrarily, if lambda tilde is larger than 1, rho star equal to 0, the disease-free equilibrium will be unstable. And on the other side, we have different possibilities, actually. Most of, in every case for lambda tilde larger than 1, sorry, one of these two stationary solutions, rho tilde, rho star or plus and minus, rho star plus will always be present, while what happens is that for big lambda, so the sum over of the infectivities over the triangles, so over the group interaction, the three-body interactions, is larger than 1 plus lambda 2, what happens is that a new region emerges with respect to the case of the SIS model. These two curves, the red one and the blue one, shows the prevalence, so rho star plus, so the stationary density of infects as a function of the infectivity with respect to the links, the infection, the pairwise infection. And if the infectivity over the triangle, so the I over the interaction is small enough, we have the same transition, a continuous one of the SIS model. Instead, if this big lambda, which is the sum of the three contagion processes over the triangles, is larger than this threshold 1 plus lambda 2, a B-stability region emerges and the phase transition becomes from continuous to discontinuous. What is important is that these curves are built for 3 different values of eta. This means that, and the other parameters are fixed. This means that tuning the amount of distrust of a network make the transition of the let me call it SIS model, even though we have more, okay, the continuous transition to be an abrupt one, a discontinuous one, in which an hysteresis loop appears, and this region between some critical lambda and 1, for this lambda tilde 1, is a region in which both the endemic state, rho star plus, and the stationary state, the disease-free state, coexist and are separated by rho star minus, this dashed line. Moreover, we can see in this model that there is a nonlinear interplay between the average connectivity of the network and the amount of trust with respect to the prevalence. More precisely, we see that for low values of the distrust of the network, increasing the connectivity, so the average K, the average number of links of the network, increasing the connectivity reduces the prevalence, while the opposite behavior occurs after this second crossing. The first one occurs at almost 0, the second crossing. And this can be seen by this subplot here. Okay, let's talk about the second part of the thesis, the second model. One thing I forgot to say, actually, that is very important, is that how do we choose the sign of the triangles? We chose the sign of the triangles by inheritance, in the sense that thanks to the fact that we're using simplicial complexes, the signs of the triangles, this 3 plus, 2 plus, and 1 minus, are directly inherited by the underlying pairwise interactions. And this allows us to write these relationships here, tau 0, tau 1, tau 2, and tau 3, thanks to the fact we're using simplicial complexes and thanks to this assumption. But it is not granted that in social interactions, the trust that I have with one individual is preserved if I interact with simultaneously with other people. This is why in the second part of the model, we relax this assumption following social balance theory, which tells us that in real social systems, actually balanced triangles, balanced interactions of 3 individuals with an odd number of positive links is favored. What does it mean? Look at these 2 pictures. We have 3 individuals with 3 positive signs. So 3 individuals that all trust themselves. This means that the friend of my friend is my friend. Look at the second one. We have 1 positive sign and 2 negative signs. This means that if I'm the person at the right, the friend of my enemy is my enemy. And this makes sense. In this case, what do we have? We have 2 negative signs or 2 positive signs or 0 positive signs. So 2 or 0 trust relationships. This leads to a sort of frustration in the social system, because this leads to the friend of my enemy is my friend. No. Or the enemy of my enemy is my enemy. This is why we said that these 2 configurations are balanced configurations that are overrepresented in general in real social systems. So what we do is that we reshuffle the configurations of the signs in our simplicial complex, in our sign simplicial complex, in a way to give preference to balanced configurations or not. How do we do that? We introduce these 4 parameters, pi, which is a bias parameter. So it's a reshuffle of the configurations of the signs of the triangles with respect to the amount of distrust that I have, which is fixed, eta is fixed. And we define the new parameters for the average numbers of triangles with 0, 1, 2, or 3 positive in the positive signs by multiplying the older ones, which is the directly inheritance, but these biases, P0, P1, P2, and P3, which are positive or equal than 0. Note that for all parameters equal to 1, we recover the same exact model as before. And what we do is we also know that these 4 parameters are not independent because the sum over the average number of triangles is fixed and equal to the average K triangle. This means that if I fix P2 and I take P1 equal to P3, for each value of P0, I will uniquely determine the value of P1 equal to P3, okay, while I'm fixing P2. Note that also P0 and P2 represent the unbalanced triangles, while P1 and P3 represent the balanced structures. What we see is that if we plot 2 different curves, or P0 equal to 1 and P0 equal to 5, so for low bias of the unbalanced triangles and high bias of the unbalanced triangles, P0, we have a counterintuitive actually behavior in the sense that these 2 curves cross themselves. What does it mean? It means that for low values of the infectivity through the links, the prevalence, the stationary density of infects of unbalanced structures, so for P0 equal to 5, the blue curve, is lower than the one for low values of P0 equal to 1. The opposite behavior occurs for large values of infectivity, actually, in which the blue curve is above the red one, and so it means that more unbalanced triangles lead in the stationary state to a higher stationary density of infected individuals. Not that in a real social system we would be more likely to bet on the red curve because we expect more balanced structures rather than unbalanced. In the end, what we did also is not only this analysis allows us to compare the weight, the proportion weight between the balanced structures of the social network, so triangles with the odd number of positive signs, and unbalanced ones. But we can also analyze the behavior within the balanced structures and within the unbalanced one, in the sense that which is better between the one configuration above and the one configuration below. These are the unbalanced one. Which is better between these 2? What do we do here is to fix, as always, as before, P1 equal to P3 and covary P0, P2, because they, thanks to the relation, to the interconnection of the last line between these 4 parameters. And what we see is that in the top panel, rho star increases with P2 in the sense that the prevalence is high when we increase the number of triangles with 2 positive signs with respect to the one with 0 positive sign. So it means that the upper reaction, the upper interaction has more weight, leads to a higher prevalence. And this is due, these processes are due to a high nonlinearity of the process, actually. While in the other case, for P0 equal to P2, if we covary P1 and P3, so the balanced structures in the bottom panel, we see that rho star increases with P3, actually, the stationary density, and a B-stability region emerges. So what does it mean? What did we find out in these 2 variants of the model? We found out that not only higher order interactions can lead to an abrupt phase transition, this continuous one, from a continuous one of the SIS model, and this was known, but we found out that tuning the fraction of distrust relationships in our networks induce B-stability, coexistence between stationary, between disease-free and endemic state of the social epidemics, and also the way in which these signs, the relationship are distributed, is crucial for determining both how much is the prevalence, the stationary density, and how fast will the transition occur. So how the critical lambda, so the point of each curve on this sort of parabola, is exactly. Further perspectives of this work are that we can use less strict approximations to analytical analysis work. Rather than non-homogeneous, we could use an heterogeneous network and heterogeneous mean field. We could use temporal networks or consider large group structures, as I said before, for example, groups of size 4. I would like to thank you deeply the work done by Jean-François, Luca, and Professors Latora and Carletti, and I would like to thank you for the attention.